All right, so I put 2, 6, and 2, 7 together. They are both about rational functions, okay, and their asymptotes. 2, 6 is vertical asymptotes, horizontal asymptotes, and then 2, 7 is slant asymptotes, so we'll get to all of it. We'll also get to holes. These are topics that we talk about lightly in Algebra 2, so hopefully this is not completely foreign, but we're definitely going to get more specific in this section, or the next 2 sections. All right, we start with what is a rational function. So rational functions are quotient of polynomial functions. This means rational functions can be represented as a fraction where one expression goes over the other. Those are individual polynomials. So this could be an x to the second, this could be an x to the first, this could be an x to the third in the numerator or the denominator or both. Just like every other fraction, the denominator cannot equal 0 because then it would be undefined. And the domain of rational functions is the set of all real numbers except the x values that make the denominator 0. So one of the very first things we will do when we get our expressions is to find the domain by setting the denominator not equal to 0, okay? And then we're going to learn how to find zeros, holes, y-intercepts, slant asymptotes, vertical asymptotes, and horizontal asymptotes, all from these equations. So obviously, quick domain review, okay? We've done this a couple times, but the domain of a function is all real numbers except if one of these 3 cases happen. There's a variable in the denominator, and for that we set the denominator not equal to 0. There's a variable under a square root, and for that we set the expression under the square root greater than or equal to 0. Or the combination of them, square root in the denominator, and so now we set what's underneath the square root greater than 0. What's going to happen in this section is the first one. There will be variables in the denominator, so we will set them not equal to 0. We will also give this in interval notation. So if it said x cannot equal 3, then from negative infinity to 3 and 3 to positive infinity would be my domain. All right, so example 1, find the domain of the rational function. We're going to set our domain, denominator not equal to 0. And I get x cannot equal 4. And so our domain is negative infinity to 4, union 4 to positive infinity. So for domain, we don't worry about anything except the denominator. You do this one. What are you going to have to do first? Well, what's one option of what you can do first? You can factor it, right? Or you can move it in square root, but you got to use your even root property. So either of those work, but you got to choose the even root. Don't forget your plus and minus. All right, so again, we have 2 options, x plus 6, x minus 6, because it's the difference of 2 squares. Can't equal 0, can't equal 0, so x cannot equal negative 6 and x cannot equal positive 6. Or x squared minus 36 can't equal 0, so x squared cannot equal 36, and x cannot equal plus and minus the square root of 36, which gets you the same answer. Either one works. Then negative infinity to the first one, which is negative 6, union first to second or smaller to larger, union 6 to positive infinity. Raise your hand if you got it right. Okay, good. Questions? All right. So these we're just going to graph using our initial transformations, and these are going to give us somewhat of an idea of what these graphs will eventually look like. It says graph the parent function and the transform function. It's been a long time since we talked about this, but the parent function of 1 over x is up in the top right corner and in the bottom left corner like that, almost like an L shape. There's a vertical asymptote at 0 and a horizontal asymptote at 0 for that parent function. So if I do plus 3 in the bottom, that's like having plus 3 in parentheses. What kind of shift does that occur? Or does that cause? Other way around, to the left, right? To the left, right, but yes, to the left. So 3 to the left means my vertical asymptote now shifts left. Still same horizontal asymptote. And then my curve would be top right and bottom left. We're going to get way more specific than this, but this can give you an idea of what they look like. Now think about the domain on this guy. What would be the domain? X could not equal what? -3. Look what's happening at -3. There's a vertical asymptote. So that's what's causing that break in your graph. All right, then f of x equals 1 over x minus 2 plus 1. The minus 2 in the bottom causes what?
X cannot equal 2.
It will be x cannot equal 2. What kind of shift does it occur?
Right 2.
Right 2. And the up, or the plus 1 is your up 1. So now I went right 2 with my vertical asymptote, which is consistent with it can't equal 2. And it goes up 1 with my horizontal asymptote. And then the curve goes top right, bottom left. So again, these are just approximations. We're going to get way more specific. But if it is in that standard form, it can give you an idea of what it would look like. Questions on that one? All right, so vertical asymptotes occur when the denominator is equal to 0. So in this case, I would have a vertical asymptote at x equals 0, and there it is. It's running right through my y-axis. The graph cannot cross through or touch anything the vertical asymptote, okay? It cannot cross through it. It cannot touch it. It would be undefined. The horizontal asymptote is a different concept. The horizontal asymptote is more of a guide for the end behavior. It can cross through a horizontal asymptote, same for slant. But for vertical, it cannot. There can be 1, there can be 2, there can be 3. It's for as many times as you would get an x equal to 0 in your denominator. This notation, okay. Oh, thank you. You're so helpful. This notation, this little arrow notation, and you won't be tested on this, but you could see this when you start to look at things with asymptotes. This is heavy for AP. That little notation, x arrow a plus, means as x approaches a from the right. And then the one under it, x arrow a minus, is x approaches a from the left. And then under that, x arrow infinity is x approaches infinity, and x arrow negative infinity is x approaches negative infinity. So a lot of times they will use these when describing vertical or horizontal asymptotes or the behaviors around them, like this guy. So notice these curves are both in my numerator. That's usually what happens if it's an x squared, okay? But not always, depending on what the numerator is. And basically, you just have to understand this notation. That top left box says, as x approaches 0 minus, which means as x comes towards 0 from the left, the f of x approaches positive infinity, meaning this value is going to keep getting bigger and bigger and bigger without bound, meaning it's never going to stop. If I go to the one on the right, it says as x approaches 0 from the right, because that's the plus. So I'm saying as I get closer to 0 from the left, f of x also points to positive infinity or increases without bound. And then these bottom mean the opposite. As x approaches negative infinity, so now we're saying as x goes to negative infinity, and I don't need a direction here because I'm going to negative infinity. There's only one way to get there. The f of x approaches 0. So there is a horizontal asymptote at 0. It's not going to touch 0, but it is going to get as close as possible. And the last one is x approaches positive infinity. So as I'm getting closer and closer to positive infinity for my x values, the graph also approaches 0, okay, which it gets closer to 0. Again, you won't be tested on that. That's, like I said, that's like heavy. That's like AP loves this content, which is what we've been working on a lot. But that is something that you might see should you start to look at asymptotes, and you need to understand the verbiage. All right, so we're going to start by step 1, domain, 2, vertical asymptotes. To find the vertical asymptotes, the notation for vertical asymptotes is as f of x approaches infinity or as it approaches negative infinity, means what's happened at the top. The x is approaching a from either the left or the right. So if x equals a is a vertical asymptote, then as x is getting closer to a, it's either going to go to positive infinity, or as x gets closer to a, it's going to go to negative infinity, which we're going to figure out in a little bit. And that can happen on either side. The horizontal asymptote affects the end behavior of this graph. So as, let's say there's a horizontal asymptote at 0, as x approaches positive infinity, it's going to get closer to that horizontal asymptote. Either it's going to come from the top or the bottom, but it's going to get closer to it. And reverse, as it goes to negative infinity, it's going to get closer and closer to it. But it will never, well, this one can cross through if there's a middle behavior, but we're going to talk about that in a little bit. So here's 3 examples. The one on the left actually has 2 vertical asymptotes, and it causes 2 curves on the outside, which can either both be up, both be down, or alternating. And it causes a graph in the middle, which can be cubic shaped like this one, or it could actually be a parabola too. If there's only one vertical asymptote, then it's going to be in the corners like this one, top right, bottom left, or top left, bottom right. Or like the one we saw before, they could both go up, or they could both point down. There's all those options. And then we won't cover too many like this, but all the way at the right, it has no vertical asymptotes. So it does have a horizontal, because the one on the right is getting closer to that horizontal. The one on the left is going to get closer to that horizontal. But there is, actually it's lower, but it's fine. But there is no vertical asymptote, so there's no break in your graph. We will do more of these and these than that last one. Just know it can exist. Now this is horizontal asymptotes. So if I have a horizontal asymptote, there can be one where it approaches it on either side. There can be one where it gets closer to it from both directions. And there can be none, like the one at the end. There cannot be more than one horizontal asymptote. So you can't have 2 horizontal asymptotes, where like vertical you can. All right. This is how we found the vertical and the horizontal. This is probably the most important slide in the whole notes. So the vertical asymptotes occur where the denominator equals 0. So if I'm going to set denominator equal to 0. If you've already found your domain, then instead of saying not equals, we just say equals, which is what we'll usually do. These are x equals a number. You have to have the x equals because these are equations. And then horizontal asymptotes occur in 3 ways. N and M represent the highest exponent in the numerator and the highest exponent in the denominator. So N for numerator, M for denominator. If N is less than M, then there's a horizontal asymptote at y equals 0. If N is equal to M, then there's a horizontal asymptote at the leading coefficient of N, or your numerator, over the leading coefficient of M, or your denominator. Notice these are both y equals equations. Again, has to be an equation. And then the third case is there's no horizontal asymptote, and that happens if the highest exponent in the top is bigger than the highest exponent in the bottom. How many of you remember this slightly from last year? We did asymptotes at least. Okay, all right. All right, so example 3, find the horizontal and vertical asymptotes, if any, and then we're of the graph of the rational function. So look at A. So for my vertical asymptote, I do what? Set the denominator equal to 0. So I get x plus 6 and x minus 6. Split and solve there, and I get x equals negative 6 and x equals positive 6. There are 2 vertical asymptotes. No, horizontal can only have 1 or none, but vertical can have an unlimited amount. You're welcome. All right, what's the highest exponent in your numerator? 1. What's the highest exponent in your denominator? 2. What's the relationship between n and m?
N is greater than 1.
Other way around. N is less than m. So if the numerator's exponent is less than the denominator's, then what's my horizontal asymptote? Good. You have to memorize those 3 options. All right, you do the rest. All right, so for B, vertical asymptote, you can either factor it or use even root, but you should get x plus 2 and x minus 2, which means the vertical asymptotes are at x equals negative 2, x equals positive 2. Again, has to be x equals. Like, that's something that you would lose points on. That would stink. Don't do that. And then your horizontal asymptotes, we look at the exponent in the top and the bottom. In this case, they're the same, which is our leading coefficient one. So we put the leading coefficient of the numerator over the leading coefficient of the denominator, and 3 over 1 is just 3. Raise your hand if you got it right. Good. All right, C, denominator, if I set this equal to 0, first of all, I can't factor it. If I set that equal to 0, I end up with x squared equals negative 1, and I get x equals plus or minus the square root of negative 1. Is that a real number? No. So this means there is no vertical asymptotes. That's how that would happen. There can still be, God bless you, there can still be a horizontal asymptote. So highest exponent in the numerator is 1 in the denominator. 2, that means that there is a horizontal asymptote where y equals 0. When the top is smaller than the bottom, it's at 0. Good? So we're like gonna compound this all. We're gonna do domain, vertical asymptote, horizontal asymptote, and then we're gonna add to it. So there are things called holes in your graph. This is a really wordy slide, but I just want to point out the super important part, which is that a hole occurs if you can cancel a factor from your numerator and denominator. So now step 1 is always gonna be factor, both the top and the bottom. So if I had this expression and then I factored the top and the bottom, it would look like this. If I can cancel, which in this case we can, a factor from the top and the bottom, we actually eliminate the vertical asymptote there and we create a hole. So it changes what your graph looks like and it introduces what's called a hole, a literally open dot. So the new equation for this one would be y equals x plus 2, and that's a line, so that's why you see this. But there is a hole at the factor you crossed out. So if we crossed out x minus 2, then we would have a hole at x is 2, which is where this is occurring. To find the y point or y coordinate of that, we would plug that x back into the simplified expression. So I would come back up to this guy and I would say y equals 2 plus 2, y equals 4. And that's how I know the coordinates of that hole, 2, 4. With a line, you can count slope. It's not so hard to find that if you wanted to count slope, but they won't always be linear after you get a hole, okay? They could still be one of the rational shape functions, and that's when you want to make sure you'd be able to identify a hole. So now every time we do a function, we're going to check for a hole. We're going to factor it. We're going to find the domain first because domain is not impacted by a hole. So we're going to factor. We're going to find domain. Then we're going to check for a hole. Then we do vertical asymptote, then we do horizontal asymptote. So that's all here. And symmetry, I would say it can help, but it's not going to be required. So obviously it can help because if I know it's symmetric to the y-axis, whatever's happening on this side is going to happen on that side, and then I don't have to plug in some extra points. If it's symmetric to the origin, then I know whatever's happening there is happening here, and again, it eliminates the extra work of plugging in points. So symmetry can help, but it's not going to be like a question on your quiz or test. Yeah.
If there's symmetry, there can't be a hole on one side.
It would have to be on both. Yep. Good question. Yeah. So I'll be honest, the order here I don't go in. The order here I go in first, factor. Then do domain. By setting your denominator not equal to 0. So factor and check for holes, obviously. But first, factor. Second, domain. 3, check for holes. 4, find vertical asymptotes. 5, horizontal asymptotes. 6 and 7 really don't matter, but 6 is x-intercepts or zeros. 7 is y-intercepts. And then you're going to plot all that stuff on your graph. And you're going to plot any extra points. So at least 1 point beyond and between each x-intercept and vertical asymptote. So in each range, you need at least 1 concrete point. Or you get to use your symmetry, because that could help you too. And then you're gonna graph it all. Now we're gonna just keep going on this pattern, okay? So it says graph using the 7-step strategy from the previous slide. So again, on your test, it's actually gonna, there are some that just ask for those individual parts, but then there's, I think I gave you 2 big guys that have all those parts on it. So you're gonna literally go in the same, like good practice should just start going in the same order every time. Step 1 is see if it can be factored. Can the top or the bottom be factored here? So it can't be factored, okay? So then I go to step 2, see if it can't be factored, can I eliminate a factor already to see if there's a hole? Can I cancel anything in the top and the bottom out? No. So that means no holes. So like if there's lines on the side and there's one that says hole, I would write none. Because that could happen. Then I go denominator. Cannot equal 0, x cannot equal 2, and that's domain. Negative infinity to 2. Union 2 to positive infinity. Immediately after that, I can do my vertical asymptote. All I have to do is change the not equals to the equals to. So if the domain is that it can equal 2, the vertical asymptote is that it does equal 2. One leads to the other. Horizontal asymptote. What's the relationship in the exponents on the top and the bottom? Same. So this is my leading coefficient. Y equals 5 over 1 or 5. Good so far. So let's start with that. Vertical asymptote at x equals 2. Horizontal asymptote at y equals 5. Now I need my zeros or my x-intercepts, and that comes from my numerator. Technically, I'm doing 0 equals 5x over x minus 2. But the very first step every time would be to do what? Multiply by the denominator. And if 0 is on the other side, what's going to happen every single time? It's going to go away. So we literally ignore the denominator. We check it for holes, but then we ignore it to find the intercepts, okay? And I'd get 5x equals 0, so x equals 0 is a 0. Or 0, 0 is an intercept. You can write it either way. Now I know it crosses through my graph here. Then I would want to find my y-intercept. And how do I find a y-intercept? Plug 0 in for x. So 0 goes here, 0 goes here. I get 0 over negative 2, which is 0, which is consistent with a 0 of a 0, right? Because they would be both. Which means I have no other points to help me. Yeah.
When you plug 0 in for y, is it because 0 was one of those zeros? Or is it
No, it's because the y-intercept, you make x 0.
Okay.
Yep. So now think about what happens on one of these graphs, okay? It's got to be in these corners. It's either going to be in opposite corners, and I know for sure it's in this corner because it crosses through 0. It's definitely in that corner. So that means it can either be next to it or it can be up here. They're never going to be stacked one on top of the other. Why wouldn't it be here? What are these things called? Rational functions. It would fail your vertical line test. They're never stacked on top of each other, okay? Does that make sense? So now I just got to figure out if it happens on the other side. Now I can use the opportunity that I was given that has no x-intercept on that side. If it's not going to cross through here, where does it have to go? Above it, right? The opposite corner. Now, how do I know for sure? I literally plot a point. So I'm going to pick a point from the range that is to the right of your vertical asymptote. So I can pick any of these points. Go easy on yourself. Make it small. So I'm going to plug in 3. I get 5 times 3 over 3 minus 2. And I get 15 over 1, which is consistent with my graph being above that axis, or above that asymptote, and not below it. Yeah.
What was the first reason you gave on why it couldn't be next to it?
Because it didn't have a y-intercept, an x-intercept here. If it's below that, it's going to have to cross through here at some point, and so it would have another x-intercept. Questions? Let's do it again. Step 1. Factor. Can the top be factored? No. Can the bottom be factored?
Yes.
Yes. X plus 5, x minus 5. Can anything be canceled out? No. So, no holes again. We'll get there eventually. But not yet. Now, domain, set your denominators not equal to 0. X cannot equal negative 5 or positive 5. So negative infinity to negative 5, negative 5 to 5, and 5 to positive infinity. And the opposite of those are your vertical asymptotes, which are x equals negative 5 and x equals positive 5. Then comes horizontal asymptote. What's the highest exponent in the numerator? 2 in denominator. 2, so this is another leading coefficient one. It'd be 2 over 2. And then come your zeros. So if I set my numerator equal to 0, I get 2x squared equals 0, x squared equals 0, and x equals plus and minus the square root of 0. So what is my x-intercept, or what's my 0? 0, but what's the multiplicity on it? 2. Why is that important? It's going to bounce. So all the rules you had about multiplicity before still stay true now. So I have a 0 at 0. And just a reminder for yourself, so I'm not going to mark you wrong if you don't include it, but when you go to graph it, it should help you, okay? That there's a multiplicity of 2. What's going to be my y-intercept? If I plug in 0, I get 0 again, right? If a 0 is a 0, then the y-intercept is 0. Now let's plot what we've got. So vertical asymptotes at negative 5 and positive 5. Horizontal asymptote at y equals 2. And only one 0 at 0, and it's going to bounce off of it, which makes me think it's going to be that parabola shape. Does it cross through the x-axis again? How do you know that? There's no other zeros, which means where do I think it's going? In the top right corners. It can't cross through here, which means it's coming up here. And it can't cross through here, which means it's coming up here. Yeah.
Can it ever be in the middle?
What do you mean? Above it?
Yeah.
No, it would fail your vertical line test. It can take on this shape, but then it wouldn't have a multiplicity of 2. It wouldn't bounce. And if it takes on that shape, they go in opposite corners. So that's where symmetry helps you. Because think about this. If I plugged in a negative x, it's going to go away. If I plugged in a negative x, it's going to go away, which means this has y-axis symmetry. So that should also confirm it's happening opposite corners the same. Does that make sense? Like they're both up because of y-axis symmetry. The parabola is happening because of y-axis symmetry. So that can help you. If it doesn't, it's not something you pay attention to, now you're going to end up plugging in some extra points. So if I plugged in 6, I would expect it to be bigger than 2. And it would be, if I plugged in negative 6, it would be bigger than 2. And it would confirm my shape. So the more comfortable you are with the symmetry and the shapes of these things, the less points you're going to have to plug in. If you don't know those things, now you're just gonna, it's fine. You can just plug in the extra points. Does that make sense? Yes? Is there one?